Okay, I will discuss today reinforced concrete beam design using, again, BS8110 standard. Okay, so you start with your design in like sizing your beam. So how will you come up with like the section of your beam? So for example, how will you, let's say, get the H and then B here? If you are, let's say, this is will be your effective depth, right? Okay, so you can use this approach. You have this table 3.17 for the effective span and then depth ratio. If for example, you have simply supported, you use 12. If you have continuous, you use 15. In this case, for this example, this is a simply supported beam. So let's say your span is 8 meters. You just divide it by 12. You can have 670 millimeters. So this is just to get the D. For example, this is around 50, 40 cover, and then 10 millimeters is your 20 is your diameter, so half of it is 10, so that's 50. If because your cover here is around 40, so if your D is, let's say, 670, maybe you can assume 700. So the total thickness or the total depth, total height of your beam has to be 750. Okay, this is just example. Okay, so your B, okay, for your B, you can assume 200, just like of your thickness of the wall, or better to use 250 to 300. Okay, so once you have the section of your beam, by the way, B could be computed in this way, okay, but you can also do like this. So this is will be your shear, which you calculated out of your reaction. Is just the total load over 2, okay, and then you have the depth, effective depth, is 670, and then you can assume your allowable shear stress, so you can get B. But then, as I said, you can just go straight with the assumption of your B. Okay, the load determination is very important. Okay, so for example, this is your beam. Okay, you're going to carry half here and also half here. The span is 5 meters, so that becomes the width of your slab that is to be carried is 3 meters, because it is 1/2 here and then also 1/2 here. So you have to, for example, this is your slab, okay, and this is your beam, okay, this is 3 meters, okay, this has to be carried by the beam, and then you're going also to compute the dead load here, the self weight, and then also this one. So first, compute the dead load of the slab. Let us say your thickness is 0.8. So what you need to do is just multiply 24 and the thickness of the slab and the width. So you have 0.8 and 3 meters. Okay, this is 3 meters. The thickness of this slab, let us say this one is in your assumption, in your design of slab before. Okay, you have already 0.8 in meter. Okay, so you can use it. Okay, so it must be that you have already designed your slab prior to this one, so you have already identified the thickness of your slab. Okay, so this is in uniform load. Okay, and then dead load also for the beam, or the self weight for the beam. You just have to multiply by the total height of the beam and then its width. So for example, here I just made an example. Let us say my beam is 0.6 and then I have 0.25. So this is the section. Just multiply with the unit weight of the concrete, then you can get this one. Okay, the weight of the beam, this one, and then weight of the slab has to be added, so that becomes the total dead load of the beam. Okay, 13.5 and 3.6, this becomes your dead load. Okay, live load has to be taken from the table. For example, this one is bedroom in the dwelling units. This is 1.5 kilonewton per square meter. Okay, there are different occupancy or type of occupants that you are going to check from the table. Okay, so you have 1.5 multiplied by the width. You can calculate the uniform weight. So 1.4 dead load and then 1.6 live load. This is from the British standard. Dead load has is already computed, 17.1, and then live load you have from the table, which is 4.5. There you have the uniform load, ultimate, the factored uniform load. This is important because we just need to calculate for moment, okay? Moment that you need for your uh, identification of reinforcing bars, okay? In the case of your assignment, I've already given to you particular values or formula for getting the moment, but basically you need to have moment distribution depending on the load acting on your continuous beam. So in this case, you just use that formula, okay? Okay, so now this is an example how you're going to start with the design of your beam. So I have already discussed earlier how you can get the uniform load, and then you compute the moment. This could be this method or this one, okay? This is the moment for simply supported, okay? In the actual one, you do it by moment distribution, okay? This part I've already presented earlier. For example, you get the uniform load of 29.6 kilonewton meter. You don't use this one because this one is simply supported. You can use this one if you have simply supported, okay? But if you have continuous beam, of course you use the formula, okay? The formula is already reflected in your assignment, okay? But for those listening to this, okay, you can use other methods on how you're going to get the moments, but given that you already have this moment, this one will lead you to identification or calculation of your reinforcing bars. In the British standard, there is a need to check for the resistance of the actual beam capacity of the beam. So that means this one has the capacity of the beam has to be greater than the design moment. The load that is actually being transmitted to the beam. Otherwise, that becomes doubly reinforced beam if this is bigger than the capacity or the resistance, okay? So let's continue. So once you get the moment, there you can now calculate what is K. This is just a repetitive approach. In my previous videos, you can watch how it's going to have like this, okay? So this is the formula that you need to use in the British standard. You need to calculate the Z, and in the Z, this value has to be compared with this one. This one should be the maximum. In other words, choose between the two, which is smaller, okay? So we use this one, and then we have it here to compute for the total area requirement of the reinforcing bars for your beam. We design the midspan, so meaning this reinforcement should be at the bottom. So looking at the table for you to get your number of bars, here you see number of bars, pieces of bars. So the requirement is 1078. Let us say initially we have assumed that we can use 20 millimeter diameter. So out of this 1078, this 1260 is the next one higher, just to sufficiently could provide the requirement of 1078 square millimeters. You don't go to for 5070, it's not economical. 943 is not sufficient. So meaning your bar here, if this is your beam, you have here 4 pieces, 1 2 3 4, okay? 4 pieces of your 20 mm diameter. Okay, once you have that one, for the example, for your assignment, I give already formula, okay? This is at the midspan, and then at the support. So your design approach is just perfectly the same when you design support and when you design at the midspan, okay? The difference only is the factor or this formula, okay? In your case, when your W is kilonewton per meter, take note that this one WL should be squared, okay? L should be squared. But if you get a total load of W in kilonewton, you can use this WL, okay? Again, kilonewton per meter, L has to be to the power of 2. Okay, so these are the design steps that you're going to follow. Design criteria and load determination. Then you take at the midspan, calculate the moment, and then AS, and then you identify the reinforcement. At the support, it's the same. You calculate the moment, you compute the AS, and then you identify reinforcement. From there, you check the stirrups, you check the deflection, and then show the drawing details. Now let me present to you some example of how you can calculate the shear reinforcement. I have 2 examples that I'm going to present to you here just to show the difference, okay? When your imposed load is 0, meaning there's no live load, and then when the live load or the impost load is 10 kilonewton per meter. So let us see first example. Okay, from this familiar table, you're going to compute this one. Your value becomes 1.1. Okay, so here meaning you are going to do interpolation. So if you do the interpolation between here and then this one, because our depth is more than 400, so it should be in between 0.63 and 0.72. So from this interpolation, you can compute that value of x, which is that VC, okay, which is 0.65 or 648. So it is somewhere between 0.63 and 0.72. It's somewhere here. This is that 1.1. Okay, we need this one to compare. Okay, let us compare, which you have V in the beam. It's only 0.5. Okay, it's only 0.5, and the slab has like this. When you have this condition, meaning there's no requirement for your stirrups. Now let us check. Okay, your V that we have calculated is this one 0.24, right? This one is 0.24. This is it. 1/2 of VC from the table that we had earlier is 0.65. It's 0.32. So meaning it is less than. Okay, meaning it satisfies this condition. Okay, so meaning there's no link. It is understandable because our live load QK is equal to 0. Now let us try when our live load is 10 kilonewton per meter. So there's a big live load occupancy. So we see again the reaction out of this one. Let's say dead load is 10, live load is 10. You have 180 kilonewton. Your shear, okay, is just 1/2 of the total load. Okay, and then B, for example, in this example, okay, just remember this is different to the previous example. So in this example, your B here is 325, and then your D is equal to 547. Okay, when we say D here, it's always the effective depth. When you substitute here, this is the actual shear stress, 0.51. Now take note that earlier 1/2 of VC is just what's that, 0.32. So meaning this doesn't satisfy this one. Okay, there's a need for link or for stirrups. So as you see here, 1/2 of 1/2 of VC is 0.32. What we have calculated is 0.51. This VC plus 0.4 will give us 1.05, meaning this condition is satisfied. Therefore, we can calculate the requirement for stirrups using this formula. Let us have this big screen. Okay, so this is it. Okay, we just have to get what is this ASV over SV. So meaning this SV, we put it down here. So we have this one. So the formula is just this one. Okay, okay, so you have 0.4. B is the base or the width of the beam, 325. 0.87. If Y is just either 500 or 250. So we calculated 0.298. Now how we are going to identify, okay, how are we going to identify our stirrups? Okay, take note, okay, the spacing of the link should not exceed 0.75 of D. You have to remember of this one. Okay, in this case it should not exceed 410. This one should be the bigger value of your maximum value of your spacing. Okay, now let us say you have 0.298 here. Okay, if we use 8 millimeter diameter from out of here, okay, what is it that satisfies 0.298? These are all bigger values. Okay, the smallest one is 0.335. In other words, in our stirrups, if this is the beam, the stirrups here, okay, this is 8 diameter spaced at 300. Okay, so for example, if you use 10, still this is the smallest one. Okay, for example, if you have values of ASV over SV, like you have 0.49. If you have 0.49, you could use 8. Let us look from here. Okay, 0.49, you could have this one, meaning 8 by 200. You can have 8 spaced at 200. Now if you use 10 diameter, What is it that would satisfy 0.49? Looking at here, 0.49. Okay, we have this one. Okay, so if you use 10, your spacing should be 300. Okay, so I hope you understand this. If you have question, just drop your question in the comment. So you have this simple details, and then after checking the shear, now deflection. Take note that the deflection, the actual deflection is just span over effective depth. For example, in this case, this is your actual deflection. You compare it with your permissible. Permissible is just this basic ratio. It could be 2620. Check your previous check the previous video or design in one way and always lab. 26 is this is for continuous support. Continuous support. If you have simple support, it's 20. This has to be the modification factor using this formula. Okay, that has a limit. Okay, it should be less than or equal to 2. In other words, if this value, for example, is 2.5, you should not exceed 2. Meaning, if you have 2.5, you're going to use 2. In this case, this is 0.97 is fine, so you can use it 0.97. Okay, so your permissible is 28, your actual is 15.56, so everything is fine for your design. Okay, so that's all for today's video. This is the sample details that you can use, or you may have some other details that could be presented in table or simple section of the midspan and then support details. So that's all. Thank you.